Greetings, everyone. This is Professor Roman. Let us continue the group theory lectures. We now come to something I imagine many of you have been waiting for, and that is a discussion of the Celo theory, a proof of the famous Celo theorems. First, however, I do want to backtrack just a tiny bit and mention something concerning the class equation. Should have done it earlier. I didn't realize that it would be useful for the Celope theory, so I'm doing it now. My apologies. As you will recall, if a group G acts on a set X, then this is the class equation. Here, as is often the case, it's customary, I've separated out the stable elements of the group action. That means that each of these indices is greater than 1. Now, if G is a P group acting on the set X, then each of these indices is a power of P, divides the order of the group, which is a P group, but it's not P to the 0, because these are greater than 1, therefore each of these indices is divisible by P. It follows then that these two values are congruent mod P. The size of X is congruent to the size of the stable set of X mod P. And that's going to be useful for us very soon. Throughout this chapter on the Celo theory, I'm going to assume that P is a prime number, because occasionally I may forget to say that, so now I'm covered. I'm also going to assume that all groups G and all sets X are finite, unless I mention to the contrary that they're not. In 1872, the Norwegian mathematician Peter Sylow, or maybe it's Peter Sylow, I don't know the correct pronunciation, published several theorems concerning the structure of finite groups that are now known as the Celo Theorems, although I'm going to combine the theorems into a single large theorem. I think some authors will actually state 5 Celo theorems, but I'm going to combine them into one. It's just a stylistic matter. These theorems have arguably become the most famous theorems of group theory, along with the theorems of Cayley, Lagrange, and Cauchy. The Celo theorems describe the nature of a certain special type of subgroup of a finite group that are now known as Celope subgroups. And just to recall, a P group is a group in which every element has order of power of P. But we've seen that for finite groups, that's equivalent to saying the order of the group is a power of P. So let us begin our discussion with the definition of a Celope subgroup. Let G be a finite group, and let P be a prime dividing the order of G. A Celope P subgroup of G is a maximal P subgroup of G, and maximal is under set inclusion. So, in other words, it's a P subgroup of G that's not properly contained in any other P subgroup of G. I will denote the set of all Celope P subgroups of G this way. I don't think that's standard. I don't know that there is a standard notation for this set. The number of Celope P subgroups of a group will denote by n sub P of G, or just n sub P. One thing to note is that if G is a P group, it has exactly one maximal P subgroup, G itself. And so it has one Celope subgroup. And of course it has no other Celope subgroups of other prime powers. So when G is a P group, the whole Celo theory is very boring. It's only interesting when the group G is divisible by two different primes. Here are some simple facts about Celope subgroups. Number one, if a prime P divides the order of G, then G will contain at least one Celope subgroup, one maximal P subgroup, because we do know by Cauchy's theorem that G has an element of order P, and its cyclic subgroup, the one generated by that element, is a P subgroup. It could be maximal. If not, it's contained in a bigger P subgroup of G, which might be maximal. If not, that's contained in yet a bigger P subgroup of G, and so on. But if G is finite, that process has to stop. And when it does stop, you will have a Celope subgroup. The same argument tells us that every P subgroup of G is contained in a Celope subgroup. Number two, if S is a Celope subgroup of G, then so is every conjugate of S. And this follows from the fact that conjugation is an order isomorphism on the subgroup lattice, sub G. And so conjugation preserves order, and therefore it preserves maximality. We will see later that the converse of this statement is also true. That is, every two Celope subgroups are conjugate. So, if S is a particular Celope subgroup, then the family of all Celope subgroups is just the family of all conjugates of S. And that's a certain orbit, which I'll let you think about. And so we'll prove that. We'll prove all this later using group actions. Number three, suppose that P to the n is the largest power of P, dividing the order of G. Then any subgroup of G of order P to the n is a Celope subgroup. It's maximal. That we will prove also. We're also going to prove the converse. So, a subgroup of G is a Celope subgroup if and only if it has size P to the n, the largest power of P dividing the order of the group. That seems intuitively clear, maximal, largest power of P dividing the order of the group. But it's going to require a proof, and we're going to use group actions to do that. Now there are many different ways to approach the Celo theorems, and I tried to find one that would hopefully be as gentle as possible. And I think the way to do that, and it's just my opinion, is to start by assuming that the group G has a normal Celope subgroup. It may not, certainly, but if we assume it does, we'll be able to make some significant progress relatively easily. Then we can cope with the issue of groups that don't have normal Celope subgroups. So we'll kind of sneak up on the Celo theorems in that way. But make no mistake, in general, there's no reason to believe that any particular Celope subgroup of a group is normal. but we're going to assume there is a normal one. And then we can use some very basic concepts to deduce facts about normal Celope subgroups that will provide us a jumping off point for our investigation into the nature of all Celope subgroups. We need an elementary fact here, something that comes from earlier material that we've done. If we have a normal P subgroup of, let's call it N of G, and any other P subgroup T of G, then the join of those two subgroups is the same as the set product is also a P subgroup, because the size of the join, or the set product, this is a formula we did a long time ago, the product of the sizes divided by the size of the intersection, which divides the product of the sizes. Each of these sizes is a power of P, and so NT is a P subgroup. That's a rather bland fact, pretty simple, but it really is the key to an understanding of normal Celope subgroups. And here's why. Suppose N is a normal Celope subgroup of G. This lemma tells us that if T is any P subgroup of G, then the set product NT is a P subgroup. It contains N, so it has to be N, because N is a maximal P subgroup. So NT equals N, which means T is contained in N, and so every P subgroup of G is contained in this normal Celope subgroup of G. And this has several very useful consequences, as described in this theorem. So let G be a finite group and let N be a normal Celope subgroup of G. All P subgroups of G are contained in N. That's what we just proved. N is the only Celope subgroup of G. So that means that NP of G is 1. All of the P elements of G belong to this normal Celope subgroup. P does not divide the index of N in G. And finally, the order of N is the largest power of P that divides the order of G. These facts come relatively easily. You can see it's just a few lines under the assumption that N is normal. So let's look at the proof. As I say, we already proved part 1, and I'm going to leave part 2 to you. It's a one-line proof. As to part 3, all of the P elements of G belong to N. If A is a P element of G, then the subgroup generated by A, this little cyclic subgroup, is a P subgroup of G, and therefore, by part 1, lies in N, and so its generator A lies in N. So all P elements of G are in N. For part 4, P does not divide the index of N in G. Well, this group, the quotient group G mod N, cannot contain any P elements, because if AN is an element of G mod N, and it's a P element, then A is not in N, because P elements are non-trivial, but A to some power p to the k does belong to n, because an is a p element, so its order is a power of p, say p to the k. So a to the p to the k will be in n, but the elements of n are p elements. If a to the p to the k is a p element, then so is a. And that's a contradiction because of 3. The p elements all belong to n. And so if a belongs to n, then this can't be a p element. Actually, I just noticed that you can simplify this a tiny bit, not much, by using Cauchy's theorem. So I'll let you think about that. For part 5, the order of n is the largest power of p that divides the order of g. Well, if the order of n is not the largest power of p that divides the order of g, then g mod n will be, this index of n and g will be divisible by p, and that contradicts part 4. Okay. So it wasn't, terribly stressful to gather these 5 facts, assuming that n is a normal Celope subgroup. Now, while it's not always true that a given Celope subgroup S is normal in G, it is always true that S is normal in its normalizer. And so this information that we just collected will apply in that context, with G replaced by the normalizer of S. So that tells us some of this, and the rest we'll figure out. Let G be a finite group, and let S be a Celope subgroup. All of the elements of the normalizer of S lie in S. Or put another way, the only p elements of G that normalize the Celope subgroup S are the elements of S itself. There may be non-p elements that normalize S, but the only p elements that normalize the Celope subgroup are the elements of S itself, which always normalize capital S. P does not divide the index of S in its normalizer, and NP of G is 1. There's a unique Celope subgroup if and only if that subgroup is normal. Well, parts 1 and 2 are direct translations of what we just learned. Again, replacing G by the normalizer of S. So they come free of charge. We've done the work already. As for part 3, we know from this theorem that if S is normal in G, then NP of G is 1. This should be a strictly less than, a strict normality. Conversely, if NP of G is 1, then any conjugate of S being also a Celope subgroup has to be S, because there are no other conjugates, and so S is normal in G. I'm going to replace these symbols by the proper normal because they're Celope subgroups. On the other hand, this will hold also if G is a P group, so I changed my mind. We'll leave it alone. Okay. So we are very close, actually, to stating the Celo theorems. Much of this is part of the Celo theorems, and in fact I guess some of this would be considered a Celo theorem. But there is one more matter that we need to deal with, and that is to show that all Celope subgroups are conjugate. This is quite important. We do know that any conjugate of a Celope subgroup is a Celope subgroup. We want the converse. So here's at least one way to prove this. Suppose that S and T are Celope subgroups of G. Then we want to examine the action of T by conjugation on the family of all conjugates of S. And I emphasize here all conjugates, not just conjugates by elements of T, but conjugates by anything in the group. This is the conjugacy class of S in G, all conjugates of S. We want to act on that set by conjugation of elements, by elements of T only. We already discussed the action of G acting on itself by conjugation. This is T acting on the conjugates of S by conjugation. Okay? This is the clever part of the derivation of the Celo theorems, the proof, to think of this particular action. What do the stable elements look like? They're the conjugates of S that are unmoved when we conjugate by any element of T. Or put another way, a conjugate, SA, of S is stable if and only if the set T normalizes that conjugate. Conjugation does nothing. That's what normalize means. So, SA is stable if and only if T is contained in the normalizer of SA. But T is a P group. It's a P subgroup of G. And SA is a Celope subgroup. And we know that the only P elements that normalize a Celope subgroup are the elements of the Celope subgroup itself. So T has to be contained in SA. But these are both, each of these is a maximal P subgroup. So they have to be the same. So SA is stable if and only if SA is equal to T, the group or subgroup that's doing the action, that's doing the acting upon the conjugates of S. You might want to pause the video at this point and go back over what we just discussed. This is not a trivial proof by any means. And if you're new to group actions, it is a little bit stressful, that I can understand. So where do we stand? We have this action of T by conjugation on the conjugacy class of S, all conjugates of S. And we learned that a conjugate of S is stable if and only if it is actually equal to T, the group that's doing the action. So there's either one stable conjugate or there are none. But we can always take T equal to S because S and T were arbitrary Celope subgroups. S is a Celope subgroup, so we'll take T to be equal to S. And in that case, what is stable? Only S itself. Only T, which is now equal to S. So if we take T equal to S, the stabilizer of this action, we're acting on the conjugates of S by T, is just this singleton set containing S. It's the only conjugate that's stable. On the other hand, if there is a Celope subgroup T that is not conjugate to S, then that action, the action of that particular T, has no stable elements because T can never be equal to a conjugate of S by assumption. So nothing is stable. And so if T is not conjugate to S, then the stabilizer is empty. So in terms of sizes, the size of the stabilizer is either 1 if T is S, or in fact if T is any conjugate of S, but we don't need to worry about that. If T is S, the stabilizer has size 1. If T is not conjugate to S, the stabilizer has size 0. There are other cases then. T could be a conjugate of S other than S, if that exists. So I'm not saying these are the only two possibilities. But I'm saying that if this happens, then this happens. And if this happens, then this happens. But this runs afoul of the corollary I gave you at the beginning of this discussion, that when a P group is doing the action, T is a P group, whether it's S or some other Celope subgroup, it's a P group. The size of the set it's acting upon is congruent mod P to the size of the stable set. And that size is 1 if T is S and 0 if T is not conjugate to S, just as we have here. But now we've got a serious problem because this has nothing to do with our choice of T. It's simply the size of the set of all conjugates of S in G. Conjugates, all conjugates. So T doesn't even enter into the computation of this number. So how could it be equal to 1 for certain T and equal to 0 for other T's if it doesn't depend on T? Can't. So one of these two can't happen, but obviously setting T equal to S can happen. So the second condition cannot happen. T is not conjugate to S. T must be conjugate to S, no matter what Celope subgroup is taken to be T. So we get actually two things out of this. First, the size of the conjugacy class of S is congruent mod P to 1. This will be useful. Also, all Celope subgroups are conjugate to S, and therefore to each other, because conjugacy is an equivalence relationship. It's transitive. So, theorem, all Celope subgroups of a finite group are conjugate, and and all conjugates of a Celope subgroup are Celope subgroups. A more concise way to say that is that the family of Celope subgroups is precisely the conjugacy class of any given Celope subgroup. Okay, corollary. G is a finite group, P is a prime dividing the order of G. NP is congruent to 1 mod P. NP is the number of Celope subgroups by definition. Well, that's right here. Because all the Celope subgroups are conjugate, this set is equal to this set, so the size of this set is the size of this set, which is congruent to 1 mod P. NP is also equal to the index of the normalizer of S in G, and that follows from something way back in chapter 8. The size, NP is the size of this set. This is the size of the conjugacy class. We computed a formula for the number of conjugates of a subgroup. It's the index of the subgroup's normalizer. So this was theorem 8.44. Finally, the order of a Celope subgroup is the largest power of P dividing the order of G. If S is a Celope subgroup of G, then its index can be split into, so this is the index of S in G, is the index of the normalizer in G times the index of S in the normalizer. Remember, indices have that multiplicative property. But neither of these factors is divisible by P. This factor is here. It is NP, which is congruent to 1 mod P, therefore not divisible by P. And this isn't divisible by P because N is a normal Celope subgroup in its normalizer. And we proved for normal Celope subgroups that there are no P elements in the normalizer that are not already in S. So neither of these is divisible by P, therefore this is not divisible by P. And so this is the order of G divided by the order of S. So the order of S better be the largest power of P that divides the order of G. Okay, we have completed the proof of the Celo theorem, but we need to gather all this information together. And I want to add a definition to the mix here. A subgroup H of G is self-normalizing if it's equal to its own normalizer, which means nothing normalizes H except the elements of H themselves, which always normalize. Okay. So HA is equal to H if and only if A is in H. Self-normalizing groups, subgroups, are as unnormal as possible for a subgroup. Their normalizer is no bigger than the subgroup itself. Okay. This term self-normalizing, that's not my term, or I would have said so. It is a bit misleading, I suppose, because H always normalizes itself. So in that sense, it's self-normalizing. The point of this definition, the meaning of self-normalizing, is that nothing else normalizes H except the elements of H. Okay. So we gather all this stuff together and we have the famous Celo theorems, and there are 5 parts, which is why in some books you'll see 5 separate Celo theorems. I would hope that the authors that do that would, at the end, collect them all together so you can see them all at one time anyway. So that was my thought, well, why bother to write 5 separate theorems? It only took us a couple pages to gather all this together. So, G is a finite group. Let P to the n be the largest power of P that divides the order of the group. And we'll assume that n isn't 0 because we want P to divide the order of the group. Part 1. The Celope subgroups of G are precisely the subgroups of G of order P to the n. So that is one way to characterize the Celope subgroups. They are the subgroups of G that have the largest possible order of the form P to the n. P to the n is the largest power of P that divides the order of the group. The family of Celope subgroups forms a single conjugacy class, where S is any particular Celope subgroup. Pick any one you want. So another way to say this, as I said before, is that all Celope subgroups are conjugate, and every conjugate of a Celope subgroup is a Celope subgroup. This is a much more elegant way to say that sort of long-winded sentence, that the family of Celope subgroups is the conjugacy class of any given Celope subgroup. The number NP of Celope subgroups satisfies 2 properties. It's congruent to 1 mod P. That we learned from our action of T on conjugates of S. And it's also the index of the normalizer because it's equal to the size of the conjugacy class, which we learned in Chapter 8, the number of conjugates is the index of the normalizer. A Celope subgroup S is normal if and only if it's the only Celope subgroup, or in other words, if and only if NP equals 1. This we also proved, just collecting it from a previous theorem. Finally, a Celope subgroup S is self-normalizing. Its normalizer is equal to itself if and only if the number of Celope subgroups is the index of a given one in G. Is the index of S in G. Okay. If that happens, if one Celope subgroup is self-normalizing, then all of them are. That's new. We didn't talk about that before. So here's the proof. First, from part 3, S is self-normalizing. It's equal to its own normalizer if and only if these 2 indices are equal. Remember, we're dealing with finite groups. And we already know that NP, that this index is NP, and therefore this is true if and only if this index is NP. Okay. As to the second part of this, because all Celope subgroups are conjugate, if S is self-normalizing, then the normalizer of any other Celope subgroup, which can be written as a conjugate of S, is equal to the conjugate of the normalizer. That was the stabilizer relationship, the third of the three key relationships. Conjugation preserves the size of sets, and S is self-normalizing, and again we have same size conjugates of the same size. So the size of the normalizer of SA is the size of SA, therefore these two are equal, and so SA is also self-normalizing. In other words, all Celope subgroups are self-normalizing. Okay, that is what most people, this is what most people would call the Celo Theorems, plural. If I say to somebody who knows this, let's talk about the Celo theorem, they're probably going to say, which one? So be careful about that when you talk to other people. It may be that almost everybody but me thinks of them as 5 separate theorems. I don't really know. We're going to use the Sylow theory now, these theorems, to search for normal subgroups of a given finite group. We're going to apply the Celo theorems now. But I strongly suggest that before you listen to this discussion, you go over what we have done so far. This is by no means trivial. There's quite a lot of information here, and it's going to take a while to absorb, and it's going to be easy to forget some of it. I too have that problem. Okay? So I would suggest spending some time with this before moving on.